Hello everyone, I'm Yuxuan Zhao, a second-year PhD student from Chinese University of Hong Kong, supervised by Professor Bain. I'm really glad here to share our work, AutoGraph, optimizing DNA computation graph for parallel GPU kernel execution. This work is finished by cooperating with Yuxuan, Zhuolun, Yang and Bain from Chinese University of Hong Kong. Let's first have a brief introduction. The DNA deployment stack can be divided into several levels. At the top level, researchers use various deep learning frameworks to define the novel and powerful models. These models can be represented as computation graphs. High-level graph automation like operator fusion, data layout transformation can be performed to enhance the inference performance. Each operator in the graph is a tensor program. Techniques like loop tiling and rolling are popular to improve the computation efficiency. Down to the runtime level, we can rely on hardware scheduler to decide when and how the kernels are dispatched and executed. In this work, we mainly focus on computation graph automation, but we explicitly take the runtime system into consideration. The cost level automation can generate well-optimized graph for parallel GPU kernel execution. There are some previous arts on graph level and runtime level automation. A widely used graph automation approach is equivalent to graph substitution. Deep learning frameworks generally perform rule-based substitution in predefined order. Haskell takes operator definition and the specification, then automatically generates and verifies graph substitutions, enabling a much larger search space than manually designed ones. GPU support parallel kernel launch by using multiple streams, leading to better computation resource utilization. LS divides the computation into different stages and use dynamic program method to find the optimized launch schedule. Nimble supports parallel kernel launch for the whole model and leverage the ahead of time scheduler to minimize the scheduling overhead. This work only focuses on single-level automation. Can we bridge the gap between them to boost the deployment performance? Here are some challenges. First, the graph automation search space. The graph automation search space is huge. Modern DNA models can be complex and large, and the number of available graph substitutions are also very large. It is non-trivial to find the graph with optimal execution time on the target runtime system in this exponential search space. Second, the interoperator paradigm is usually ignored. Previous graph optimization methods assume the runtime system launched the kernel sequentially. Therefore, they optimize the performance by simply summing the execution time of each operator. Such cost function is unreliable for parallel kernel launch scenario, in which we can overlap the execution of operators. Directly adopting existing methods cannot achieve satisfying results on parallel kernel launch frameworks. To tackle these problems, we propose a unified approach, AutoGraph. Here is the overview of AutoGraph framework. First, the initial computation graph is divided into multiple subgraphs to enable fast automation. The dynamic programming algorithm combined with backtracking search is adopted to explore the graph automation solution. Candidate graph is low customized cost function are selected for onboard verification, and the runtime feedback is utilized to get the automation. Our algorithm and techniques can successfully solve the aforementioned problem. Most modern DNA models are too large for direct computation graph automation. An effective graph partitioning strategy is highly desired. We define the node capacity as the number of available graph substitutions, and we would like to find the node size with minimal capacity sum split the graph to preserve most optimization opportunities. This task can be transformed to a network flow problem. The entire computation graph is recursively split by its minimal cost until the size of each subgraph is less than a lower threshold. We notice that node capacity keeps changing during the graph optimization process, but it is unrealistic to frequently update the partitioning result. So we merge the adjacent subgraph to form new subgraphs if the size of them is less than the upper threshold to increase the optimization opportunities. Each subgraph now is suitable for subsequent optimization. Before describing the optimization solution for the entire graph, we first introduce the backtracking search method, which is used to optimize each subgraph. Equivalent computation graphs with different runtime performance can be generated by applying suitable substitutions. Exhaustively enumerating all the possible results is of low efficiency. We propose the mixed critical path cost in equation 1 as the selection criterion. The VC is the set of nodes on the critical paths. And the critical path is the longest path in terms of cost sum, which can be extracted efficiently via topological sort. We notice that there are numerous graphs with the same critical path cost, though the costs of the restaurants still need to be considered to make a further selection. The hyperparameter alpha here controls the critical path cost rate. In each search round, candidate graph of mixed critical path cost within beta times of the current best value are collected for next search round. Complex graph optimization can be found automatically. The critical path cost avoid forming large kernels in the critical path, preserving the interoperator parallelism. Among all the possible subgraphs, we need to perform graph substitution on an optimal graph partition sequence that leads to the best performance for the entire graph. We observe that different graph partitioning sequences share the same subsequence, and thus we design a dynamic programming algorithm to find the optimization solution efficiently. We divide the graph G into G minus P and P. The P is a subgraph generated in the graph partition process, and P is always chosen from the beginning part of current G, which can have multiple choices. We optimize P with the backtracking search method and reduce the problem to a sub-problem, finding the optimal solution for G minus P. The figure here shows the transition state in our dynamic programming plus backtracking search algorithm. At current state, P5, we can directly retrieve the solution for the sub-problem G minus P5 cached in previous step by G minus P1 minus P2. Previous method terminate before onboard measurement, lacking actual runtime information in the optimization process. To acquire such information, we implement the parallel kernel launch runtime system in our framework. The operator nodes on different branches are assigned to different GPU streams, and proper synchronization events are inserted into the stream to guarantee the data dependency. We adopt the maximum matching algorithm from Nimble to find the stream assignment, which maximizes the operator concurrency while minimizing the number of synchronizations. Based on the node-to-stream mapping, CUDA graph is used to launch the computation graph. We only sample the top K candidates with small mixed critical path cost for onboard verification each time. Candidates with improved performance are selected for the next optimization iteration. That's all about our methodologies. Here are the experimental results. We conduct our experiments on NVIDIA RTX 2080 Ti with CUDA 11 and CUDA Library 8 and PyTorch 1.7. 7 modern DN models are benchmarked. We cover 5 same models, 1 RM models, and 1 transform model. First, we show the end-to-end model inference latency results. We compare our method with multiple baselines. JIT is a package with just-in-time compilation enhancement, which is a representative sequential kernel launch framework. Nimble and LS are SOTA parallel kernel launch frameworks. We also apply Tassel to package JIT and Nimble to compare the performance. Our method consistently obtained the best result on all the benchmark models, which demonstrate the significant advantages of our framework. Compared with Tassel, our method achieves speed up ranging from 1.04 times to 3.47 times on parallel kernel launch framework. Compared with LS and Nimble, our method achieves speed up ranging from 1.06 times to 1.26 times on the benchmark models. We conduct evaluation study on different settings to validate the graph optimization and the dynamic programming method. The results demonstrate that we can improve the inference latency by performing super graph substitutions. The optimal optimization solution formed by our DP-based method leads to optimized graph is better in performance. We optimize NAT9 mobile on our framework with different batch sizes. The results show our method consistently outperform all the baselines, which demonstrate the generality of our method. Although a larger batch size provides more intra-operator parallelism, we can still exploit inter-operator parallelism and graph optimization to further improve the inference performance. Finally, we make a quick conclusion. Existing graph optimization method fails to utilize inter-operator parallelism and thus impairs system capability within a parallel kernel launch framework. We propose AutoGraph to bridge the gap, leveraging customized call function and accurate runtime information. Our method achieves up to 3.47 times speed up over previous hours. Moreover, AutoGraph outperforms state-of-the-art parallel kernel launch frameworks by up to 1.26 times. That's the end of my presentation. Thanks for listening.